Alright, so welcome back. So resuming processes within a monitor, right? So we know that processes within a monitor basically gets queued when someone issues a wait, right? So when someone some process or some function that wants to run, it will issue a wait and it gets kept in a queue until it receives a signal from other processes that are running, right? So you can imagine that at some point there will be several processes that will be in queue, right? And if one of it signals is executed in signals, which process is allowed to resume to run, right? So which process is then get to run. In this case, it's first come first serve, but in some cases this is not going to be adequate, since for example, when you are trying to implement something with some sort of priority, right? And we can use a conditional wait construct, such that x dot wait some kind of condition with a conditional wait, where c is an integer called the priority number, right? The process with the lowest number of lowest number, right, is scheduled next, right? So the lower you are, the higher your priority in this case, right? So if you're trying to implement this, then we basically allocate a single resource among competing processes using priority numbers that specifies the maximum time a process plans to use the resource, right? And so it will have a function that a process R basically or instance would issue and acquire those time slot within a specific time and would release it after a given time, right? Now we won't be concentrating much on this type of allocation, but the abstraction layer for most languages when dealing with this actually provides some kind of functions that you can use. So we don't really learn threaded programming in operating systems. Will be in more advanced programming courses, but it's nice to know that you have this ability where you can prioritize queues in such a way, right? So we're gonna skip into this and go into the concept of liveness, right? So one of the important things in synchronization is basically to have liveness, right? So what is liveness, right? Okay, so a process basically may have to wait indefinitely while trying to acquire a synchronization tool such as a mutex, lock, or a semaphore, right? So you can think about it that if you're in a queue, right, there is a possibility, and if it's not a really first come first serve queue, right, where it's not really fair, you might end up where you are in the queue for a very long time, right? Or indefinitely, right? Waiting indefinitely basically violates the progress and bounded waiting criteria discussed in basically this chapter in synchronization, right? So liveness basically refers to a set of properties that a system must satisfy to ensure a process makes progress. When we say progress here, we mean that if you are basically scheduled to run, you are able to run, right, and not indefinitely be waiting, right? Indefinitely waiting in this is one of the example of it being a liveness failure, right? Incapable of being able to run, right? So one thing that causes liveness issues, liveness problems, is basically deadlock, right? So in a deadlock, two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. Right? So a deadlock is in such a situation where we have two processes here. Let's say and each process basically P0 and P1, and each process basically calls a wait on two semaphores, right? Both initialized to 1, right? So in this case, we have a wait S and wait Q, right? So P0, for example, can call for S. It's waiting for S. It's waiting for a signal to run S. Same thing with Q, and P1 waits for Q and waits for S, right? So this one waits for S while this one waits for Q, and it's waiting for some kind of signal to be received. Both of them are basically waiting, but they can't really wait. They can't really run because they'll never get out of the wait signal, because in this case, for example, it's asking for wait S, it's waiting for wait S, but somehow waiting for a signal to be received, and that signal is signal S, right? But for P1, for example, it's waiting for Q, but it's waiting for Q, but P0 needs to signal Q. But on the other hand, it cannot signal Q because it will not receive some kind of signal S, right? It won't be receive the signal from S, right? Because that's coming from P1. And if you consider these two processes will be in a deadlock because they're each gonna wait for each other, right? So other forms of deadlock is starvation. That means it's indefinitely blocking, right? Or it's basically in a starvation, basically a process may never be removed from the semaphore queue in which it is suspended. So you can think about this as, it's not that the queue is not changing, right? So in this case, in deadlock, these two processes doesn't get to move at all. Both of them doesn't get, maybe three of them doesn't get to move, maybe four of them doesn't get to move, right? But in a starvation process, there might be other process that's running, right? And there's one process here that's still in the queue despite the other process coming in and out of the queue, right? So this obviously is a unfair queue somehow, right? Priority inversion on the hand, basically schedule problems with when lower priority process holds a lock needed by higher priority process, right? So this is when basically a queue has this priority issues, we have starvation, right? We have processes that are allowed to run first, right, because of their priority, so the lower priority ones never get to run. And if it's this is the case, you'll find that we'll end up with a starvation happening. Now the one of the ways to get out of this starvation problem is to have some kind of a priority inversion, right? We change the priority according to time, or somehow solve it via priority inheritance protocol that you can implement, right? So we're gonna stop there, and this is the end of chapter 6. We'll probably talk about some issues regarding mutual exclusion, and how synchronization can, examples of some of the famous algorithms that introduce synchronization problems. So I'll see you again next in the next recording. Bye bye.